Alrighty. We were solving this problem number 19 from section 6.3 using the method of Frobenius. And there was something that I wanted to correct so we could finish. Let me scroll down. Someone that came to me, I think that was Christine, that came to me at the end of the last class and pointed it out. And I thought it, and I felt that something was not right. So let's see. This negative x there, when I put that x inside of that summation, and that should have been x to the n plus r, because that x to the first times x to the negative 1 would just give you x to the 0. So, and I did not recognize that when I was working. A bit I was trying to work too fast because we were already past the time to go home. So I was trying to rush, and anytime I know when I rush, I always mess up. So. So let me fix that, and then we'll finish this. So here, it was only on this part here, we put that x in there, so this is just x to the n. Then here, let k equal to n. Make sure we follow those steps. For this section, there are 8 steps, and if you were not here on Monday, you can come up and get a copy of one of these in terms of the steps that we're going to use to solve. So. Yeah, we factored out the x to the r. Mm-hmm. So we did that, so that's where we are basically. And then we're replacing n with some k factor. That's coming up to be step number 2. So let me make sure that we have the right notation here. That third summation is the one that I had an issue on. And so we let simply k equal to n. So I need to replace this. So there, n goes from 0 to infinity, so does k as well. All right. And so that last summation is fine. And this is x to the k. And that's good. So they all have x to the k in them. Now let me expand this page here and see what we have. We have this x to the r that we factored out times the brackets of everything that we have left. And so that step number 2 says to replace n with some k factor. So that's what we're doing there. Step number 2. Step number 3, we're going to evaluate each summation so that each summation starts at the same value. But notice here that the first 2 summations start at k equal to negative 1. But then the last 2 summations start at k goes from 0. So I need to evaluate the first 2 summations at k equal to negative 1, evaluate it at k equal to negative 1, and then its next iteration would be k equals 0. And then that would match up with the last 2 summations here. Do you see what I'm saying? Right. So this guy, Daniel, starts at k equal to negative 1. That starts at k equal to negative 1. But the last 2 start at k equals 0 and k equals 0. So if they're counting k equal to negative 1, k equal to 0, k equal to 1, k equal to 2, and so on to positive infinity. Remember, we want to be able to write everything as one summation, but I can't do that if they're not starting at the same pivot point. So I'm going to evaluate the first 2 at k equal to negative 1, pull that out of the summation. Then I have left 4 summations starting at k equal to 0. Okay. So here, step number 3, evaluate the first two summations at k equal to -1, so that the remaining summations all start at k equal to 0. So I have that k to the r on the outside times the brackets. We're going to evaluate the first one at k equal to -1. So this is a 3 there, and this is c sub 0. -1 plus 1 is 0. And then k is -1. So that's -1 plus 1 cancels out. Just have left an r. Parentheses. This is -1 plus r, or you can just say r minus 1. And that's times x to the k, but that's -1. Then we do the same thing for the second summation, so that's plus 2. If k is equal to -1, that's c sub 0. And here, if k is equal to -1, then this is -1 plus 1 cancels out, just have left an r there. So this is times r times x to the -1. Now the remaining of the summations all start at k equal to from 0. So we'll just say plus here. So I'm going to just rewrite everything. But now the emphasis, we're starting, k goes from 0 to infinity for that first one. C sub k plus 1 times k plus r plus 1 times k plus r times x to the k plus 2 times the summation as k goes from 0 to infinity. C sub k plus 1 times k plus r plus 1 times x to the k. Then that's minus this summation as k goes from 0 to infinity. C sub k plus 1 times x plus k plus r times x to the k minus the summation as k goes from 0 to infinity of c sub k times x to the k. And let's see, this that should be c sub k for that third summation. Let's see here. That's just k plus r for that. Yeah, I think I was going on that. I didn't change everything here. This is let k equal to n. So this is c sub k. C sub k. And then this is just k plus r. Got to be more careful. C sub k times k plus r times x to the k. It's that third summation that I didn't finish correcting. first summation, second summation, third summation, C sub k, and it's k plus r. Times x to the k. Sorry about that. Christine, is that what you were mumbling about over there? Well, you can speak to me. I can be wrong too. Yes, sir. Yes, sir. Exactly. Yep. Yeah, you're exactly right, Cameron. It was just n equal to k there. So I think we're all together. It's all together lovely. Yes, Kristen. Yes, sir. Because the x to the r was independent of the summation. The summation goes as from k to infinity, or from n to infinity. So x to the r would be it'll be a constant. Exactly. Okay. So step number. So here, evaluate each summation so that each summation starts at the same value. So continuing with that, what we have is this x to the r on the outside times the brackets 3 c naught times r minus 1 times x to the negative 1 plus 2 c naught times r times x to the negative 1, and then plus this. We're going to factor out this x to the k now because they're all starting at k equal to 0. So this is the summation here of this x to the k. Looks like I need more room to put that. So let's just put it down here. Say plus this summation as k goes from 0 to infinity of x to the k, in parentheses, that 3 on the outside, don't want to lose that, times c sub k plus 1 times x plus r plus 1 times k plus r, then that's plus 2 times c sub k plus 1 times k plus r plus 1 minus c sub k times k plus r, and then that's minus, I guess I can get that up in there, minus this c sub k here. So here we were able to write all the summations as one summation. Okay. Now step number 4 says determine the values of r from step number 3. R is called the index, and collectively we call them indicial roots. Now what does that mean? Now notice the first part of this problem, this guy right here, you get this 3c naught times r minus 1 times x to the negative 1 plus 2 c naught r times x to the negative 1 plus then the summation. Now that's there to help us determine the value for R. You're going to always have that when you use this method of Frobenius. And when that happens, now how did that come about? Let's go back and retract. It came about when we were substituting N for K, and when we did that, you notice that some of the summations started at K equal to -1. You can't even have that because the values for the summation are set to go over natural numbers. So from 0, those counting numbers, 0, 1, 2, 3. So you're not supposed to even have a summation going from negative something to whatever. Supposed to really evaluate a summation, from some natural number to some natural number, or, to infinity. So we evaluated the summation at K equal to -1. When we did that, we poured out those terms. That will always give you some type of equation or expression to determine R, those indexes, always. Now, let's go back and look at it again. See up here, this summation was K equal to -1. This was K equal to -1. That was K equal to 0, K equal to 0. We evaluated at K equal to -1 for this summation. We evaluated at K equal to -1 for this summation, and we put those terms on the outside of the summation. Here they are right here. Right? From there, that leads us into step number 4, determine the values of R. You determine the values from R from the part that you extracted from the summation. All right? So here, step number 4, just do some copying. Don't want to do that. I want more than that. At the bottom. Don't know. Pardon me? No, I thought I said to add a new page. Yeah, I don't know why. Please don't ask me anything about these computers. I'm just a country guy, man. I'm used to old chalkboard, and that's my favorite thing. And so I've been complaining ever since we've had these whiteboards, and then we got this projector, and who knows what they have next. And hopefully I'll be retired and I can go home. So, if I teach after retirement, I'm gonna look for those schools that have a chalkboard, and that'll be my only stipulation. Just give me an old-fashioned chalkboard and just let me just write on that. It's better. My left hand and trying to write, it's better to have a hard surface when I write on these smooth surfaces. My writing is something in and of itself, but it's a little bit better, I think, when the surface is more coarse. So, anyway, step number 4. Yeah. That's not supposed to happen. So determine the indicial roots R. So we determine R from this first part here. So notice that the summation, that this entire side is supposed to equal to 0. Right? So we set 3 C naught times r minus 1 times x to the negative 1 plus 2 C naught times r times x to the negative 1. You know, and it's all times x to the r, this x to the r right here, but we're setting it equal to 0. You divide out by that x to the r. So I'm going to factor out what's common. Well, what's common here would be that C naught and also that x to the negative 1. So what I have left is 3 times r minus 1 plus 2r. That's equal to 0. Okay. Well, if you divide through by that C naught and multiply by an x, this implies that we have 3r times r minus 1 plus 2r is equal to 0. Just solve for r. So we have r, we factor out r from everywhere, so this is 3r minus 3 plus 2 is equal to 0. So this implies that we have r times 3r minus 1 equal to 0. So that is r is equal to 0 and r is equal to 1/3. So that, again, when we had the summation k equal to negative 1 to infinity, and that other one was k equal to negative 1 to infinity, we evaluated all those terms at k equal to negative 1. We pull that out. That part that you pull out like that, that's where you determine the value for r, those indicial roots. Now, what that will do ultimately in the end, when I write the answer, I have to represent those indexes for r here with this x to the r. So I'm going to have one solution is going to be x to the 0 times that whole summation, then plus look at the other root, or r equal to 1/3. It'll be x to the 1/3 times all those solutions there that we get. So let's see how that works out. So now step number 5, we've determined those roots. So well, I already did step 5. We factored out x to the k and wrote the summation as one summation, and I did that up here. Here we write all the summations as one, and I was able to do that because all the summations were starting at k equal to 0, so that was fine. So we did that step. So now let me show you what we have. Since r is equal to 0 and r is equal to 1/3, no need to write this first part anymore, because I know now that r is equal to 0 or r is equal to 1/3. So now I'm just going to write this summation part here. Don't forget that x to the r sitting out there. So here for this step number 5, we have x to the r times the brackets. It's that one summation now, the summation as k goes from 0 to infinity. So since r equal to 0 and r equal to 1/3, that means that I've determined the values for r. I can just now write the summation here starting at that point there. So we factored out that x to the k. It's a hard task. that's minus c sub k. So this is 3 times c sub k plus 1 times k plus r plus 1 times k plus r plus 2 times c sub k plus 1 times k plus r plus 1 minus c sub k times k plus r, and then I think it was minus c sub k. Minus c sub k. Close that bracket up. Step number 6, determine a formula for c sub k. So here we just resort back to what we've been doing for the previous sections. Bless you. So I look at what I have there in the inner bracket, set that equal to 0. So we have 3 c sub k plus 1 times k plus r plus 1 times k plus r plus 2 times c sub k plus 1 times k plus r plus 1 minus c sub k times k plus r minus c sub k. That's set to equal to 0. So here we're going to solve for c sub k plus 1. So what I have there is this c sub k plus 1. If I factor that out from here and there, I'm going to add c sub k times k plus r to both sides. I'm going to add c sub k to both sides. So we get those two last terms on the right side. What I have common with these two terms is a c sub k plus 1 and then also a k plus r plus 1. I'm going to factor out that k plus r plus 1 from here and there as well. So this is times k plus r plus 1. Now I have left in brackets a 3 times parentheses k plus r. Then there's plus that 2, and that's it. That's equal to here this c sub k times k plus r plus c sub k. Now let's see, let's simplify. This is c sub k plus 1 times k plus r plus 1. Parentheses, this is 3k plus 3r plus 2 plus 2 plus 2, 2, 2. That's equal to k plus r plus 1 times c sub k. Uh-oh. How did I go from c sub k times k plus r plus c sub k to k plus r plus 1 in parentheses times c sub k? Antonio? Is that what he said? No, I'm just joking. Yes, sir, that's all. Yeah. Just picking Antonio. My kid's Barbara's name, Antonio. Antonio, cool dude. He wears gloves when he cuts hair. I don't know what's going on with that, but anyway. I'm like, dude, is it that bad nowadays? So anyway, I guess some folk don't wash their hair, but anyway. So we're going to get c sub k plus 1 by itself. C sub k plus 1 by itself. So when you do that, we just divide both sides by k plus r plus 1. and then divide both sides by that 3k plus 3r plus 2. Now, you know, when you divide, notice that those guys right there cancel out, right? That makes it easy for us. So all we have left is c sub k divided by 3k plus 3r plus 2. Well, that's our formula. That's our formula. Okay. So step number 7, determine the pattern for c sub k for each indicial root r. Remember that one case r is equal to 0, and then for the other case r is equal to 1/3 that we found up here. All right, so this is step number, maybe I better make a new page so that this page won't be as skinny. Doesn't look so good when you go online. So, step number 7. Let r equal to 0. So we got this formula, c sub k plus 1 is equal to c sub k all over 3k plus 3r, is it plus 2? 3k plus 3r plus 2, yep. So here you let r equal to 0, so this implies that c sub k plus 1 is equal to c sub k all over 3k plus 2. So now we find those coefficients now. So when k is equal to 0, we get c sub 1 is equal to c naught all over 2. When k is equal to 1, we get c sub 2 is equal to c sub 1 over 3 plus 2. We have 5. When k is equal to 2, c sub 3 is equal to c sub 2 over k is equal to 2. 3 times 2 is 6 plus 2. We have 8. When k is equal to 3, c sub 4 is equal to c sub 3 all over 3 times 3, 9 plus 2, you get 11. When k is equal to 4, and we'll just stop with this one. C sub 5 is equal to c sub 4 all over 3 times 4, which is 12, plus 2, you get 14. Okay, so let's see. Well, c sub 1 depends on c naught, but c sub 2 depends on c sub 1. So this would be c naught all over 5 times 2, we get 10. C sub 3 depends on c sub 2, so that's c naught all over 8 times 10, we get 80. And so c sub 4 depends on c sub 3, that's c naught over 880. And then this is c naught over 14 times 880. So that first solution is this, is y equal to, you got that x to the r that you have to take into consideration, because that's that index. Then this is times c naught plus c sub 1 times x plus c sub 2 times x squared plus c sub 3 times x to the third, and so on. So this is y is equal to here x to the 0 times the c naught, which we don't know what that is, but everything else depends on it. Then plus c sub 1, but c sub 1 is c naught divided by 2. Then plus c sub 2, which is c naught divided by 10. Plus c naught all over, for c sub 3, 80. Plus c naught over 880, x to the 4th. And just say plus and so on, because my space is running out. You clean that up. This is y is equal to, now x to the 0 is just 1, so I'm going to fract out a c naught. That becomes my constant in terms of the superposition principle. So this is just 1 plus x over 2 plus x squared over 10 plus x cubed over 80 plus x to the 4 over 880 plus, we got space to put that other one, x to the 5th over 14 times 880 plus and so on. All right, so that's the first solution. Now the second solution, you have to say let r equal to 1/3. Right, we have two values for r. One r was equal to 0, the other r is equal to 1/3. So the formula, that c sub k plus 1, was said to be c sub k all over 3k plus 3r plus 2. So if you let here r equal to 1/3, so we get the formula c sub k plus 1 is equal to c sub k over 3k plus 3 times 1/3 is 1 plus 2, we get plus 3. So we use that formula now. So we say here k is equal to 0. We get c sub 1 is equal to c naught all over 3. When k is equal to 1, we get c sub 2 is equal to c sub 1 over 6. When k is equal to 2, we get c sub 3 is equal to c sub 2 all over 2 times 3 is 6 plus 3, we get 9. K is equal to 3, we get c sub 4 is equal to c sub 3, and this becomes 3 times 3, 9 plus 3, we get 12. We'll just do one more. K equal to 4. C sub 5 is equal to c sub 4 over 3 times 4, 12 plus the 3, we get 15. Now let's see if we can look at the pattern. So they all depend upon the previous one. So c sub 2 is c naught over 6 times 3. You get 18, or you can just, it just depends on how you want to write it. You can just leave it as 6 times 3, it's fine. This is c naught all over 9 times 6 times 3. This is c naught over 12 times 9 times 6 times 3. And kind of see that pattern. So 15 times 12 times 9 times 6 times 3. So then we write this solution as y is equal to x to the 1/3. You can't forget that, because that was important, that index, times c naught plus c sub 1 times x plus c sub 2 times x squared plus c sub 3 times x to the 3rd, and so on. Now we plug in those values. So y is equal to x to the 1/3 This is C naught plus, at C sub 1 was C naught over 3 times x plus C sub 2 was C naught over 6 times 3, and they all tend to have that pattern. The next one, C naught over 9 times 6 times 3 times x to the third plus C naught over 12 times 9 times 6 times 3 times x to the fourth, plus and so on. And then we can just clean that up. So we get y is equal to, here this C naught times x to the 1/3 times 1 plus x over 3 plus x squared over 6 times 3 plus x to the third over 9 times 6 times 3 plus x to the fourth over 12 times 9 times 6 times 3 plus and so on. So you can put both of those answers together and just write it as one answer. Let's do that for the next page, and that'll be step number 8. And here we got, so the last line of each one would be the final answer. And then we have to change the C naught, and you can write it one C sub 1, then the other C sub 2, and it looks just like the superposition principle. So there's nothing in there. Don't delete the whole page. Get it again. That one is there, then the other one. Is it copying everything in there? Better do that. Care about that. Okay, well. Okay, just gave me part of it. What was the other part? C naught. C naught times x. Okay, so let's see if I can fix it up here. So y sub c is equal to C sub 1 times 1 plus x over 2 plus x squared over 10 plus x cubed over 80 plus x to the 4th over 880 plus and so on, and then plus c sub 2 times that x to the 1/3. And times the brackets 1 plus x over 3 plus x squared over 6 times 3 plus x cubed over 9 times 6 times 3 plus x to the 4th over 12 times 9 times 6 times 3 plus and so on. And so that becomes the final answer, and the stuff that I don't need, if I can get rid of that. See if we can pull all that up. Jeez. I tell you, if I wasn't a praying man, I have some choice words for this stuff. In my house, stuff and crap is a bad word. You know? I got my middle son, he'll get you. And he goes around and, you know, and we gotta help him out, but it doesn't help, you know. You can't say the S word, Daddy. And so people thinking I'm saying something else, but S word to him is shut up. You can't say that. You don't like shut up. So, you know, we're at church. Don't say the S word, Dad. Don't say that to John. Hey, people, they don't, you know, they think you're talking about something else. The C word, crap, is a bad word to him, you know. You can't say shut up. You got to say be quiet or whatever, use your inside voice and all this stuff. And the terminology that I'm not even used to, you know, where I'm from. You know, get you out there and cut that wood, boy. That's what I'm used to. Get yourself out there and cut that wood. Well, so here's how the test is going to be set up. See if I can help you out with this, because you know, a problem like this guy right here in 6.3 is very long, and so what I've done on the test, and I'm going to show you just an outline of how that test is going to look. So I've taken like one problem like this, and I spread that one problem really over 3 questions on the test. So for the first part, you find those indicial roots, like you find r equal to whatever, r equal to that. You get a lot of points just for that itself. Then the next part would be find the formula that c sub k plus 1 is equal to whatever. So you'll get credit for that. And then what I did, because, you know, writing these solutions, man, that becomes a task in and of itself. Oops. So what I did to try to give you extra credit was the bonus question would be write the final answer. So that should be good. And so I think that should work out for you. Let's look at that, and I'll show you that. And then what I want to do is try to have everything today posted in Blackboard as well.